Hi, in the previous modules we discussed how MR data is acquired and images reconstructed. However, so far we've focused on a single image. In this module we're going to transition to talking about functional MRI. We'll see by how repeatedly acquiring certain types of images we can study brain function. We'll talk about some of the characteristics of the resulting signal and also its noise properties. So both MRI images and functional MRI images are acquired using the same scanner. MRI studies brain anatomy. These structural images are usually T1 weighted. They give us high spatial resolution, and therefore we can distinguish between different types of tissue, as we can see in the brain image below. Functional magnetic resonance imaging, or fMRI, studies brain function. Here we collect functional images, or T2 star weighted images, and they give us lower spatial resolution, as we see in the images below, but higher temporal resolution. So we acquire a new image every 2 seconds or so. Because we have a series of images that are acquired every 2 seconds, we can relate changes in signal to the experimental manipulation. So we can perform a task while collecting these images and try to link the task and changes in signal. An fMRI experiment consists of a sequence of individual MR images where one studies oxygenation changes in the brain across time. So for example, consider that we do a simple experiment, a finger tapping experiment, where I tap my fingers for 20 seconds and then I rest for 20 seconds. Tap my fingers, rest, tap my fingers, rest, all in 20-second sequences. Let's say that we study the signal from a certain voxel of the brain. We see this voxel here at the bottom, and we extract its intensity at each time point. If we do that, we get a time series. And what we can do is we can look at the behavior of this time series and try to relate it to the experimental paradigm, which was this periodic tapping and resting, tapping, resting. And in this particular example, we see that we have a boxcar type function which goes up and down as we tap our fingers and rest. So what are the properties of this signal that we're extracting from the voxel? Well, the most common approach towards fMRI uses what's called the blood oxygenation level dependent, or BOLD contrast. The BOLD contrast allows us to measure the ratio of oxygenated to deoxygenated hemoglobin in the blood. Now, it doesn't measure neuronal activity directly. Instead, what it measures is the metabolic demands, or the oxygen consumption, if you will, of active neurons. The reason we can do this in an MR scanner is that hemoglobin exists in 2 different states, each with different magnetic properties, and therefore each producing different local magnetic fields. This is a result due to Linus Pauling already in 1936. Oxyhemoglobin is diamagnetic, while deoxyhemoglobin is paramagnetic. And so BOLD fMRI takes advantage of this, the difference in T2 star between oxygenated and deoxygenated hemoglobin. Because deoxyhemoglobin is paramagnetic, it creates an inhomogeneity in the magnetic field, which causes the nuclei to dephase quicker, and therefore it suppresses the MR signal. So as the concentration of deoxyhemoglobin decreases, however, and we have more oxygenated blood, the fMRI signal will increase. So the change in the MR signal, which is triggered by a neuronal activity, is known as the hemodynamic response function. So basically, as neuronal activity increases, so do the metabolic demands for oxygen and nutrients. So as the oxygen is extracted from the blood, what happens is that the hemoglobin becomes paramagnetic, which creates these distortions in the magnetic field that I was talking about, and this causes a T2 star decrease, so a faster decay of the signal. Thereafter, there's an overcompensation in blood flow that dilutes the concentration of deoxyhemoglobin, and this is going to tip the balance towards oxyhemoglobin, so there's going to be a lot more oxyhemoglobin than deoxyhemoglobin. And so this is going to lead to a peak in BOLD signal that takes place about 4 to 6 seconds following the neural activation. And after reaching this peak, the BOLD signal then decreases to an amplitude below the baseline level. So this is what's called the post-stimulus undershoot. And this is due to a combination of reduced blood flow and increased blood volume. All this is summarized in the hemodynamic response function as we see here. We start out at a baseline level, and we perform some sort of task, such as clapping our hands. What happens then is that this process takes place, and a lot of heavily oxygenated blood comes to that region of the brain. This causes the rise in signal that takes place after 5 to 6 seconds, and thereafter it returns to baseline after, say, 20 to 25 seconds. Well, the magnitude of this signal change is really quite small, so it's usually between 0.1 to 5% of the signal. So it's very, very hard to see in individual images, so therefore we often repeat experiments or tasks several times and try to get an average. As we see, the response is delayed and quite slow, so extracting temporal information is really hard, but it is possible if we design our experiment in the correct way. And so even very short events, such as me clapping my hand, have a rather long response, up to 25 to 30 seconds. Now, what complicates this even more is that the exact shape of the hemodynamic response has been shown to vary both across subjects and across regions of the brain within the same subject. So we're not going to have the same HRF in all regions of our brain, and my HRF in a certain brain region might not look like yours. Bold fMRI is really an indirect measure of what we're really interested in, which is the neuronal firing. So the natural question that one can ask is, well, how well does this bold signal reflect increases in neuronal firing? Well, it's been shown that the bold signal corresponds relatively closely to the local electrical field potential surrounding a group of cells. And this in turn is likely to reflect changes in postsynaptic activity under many conditions. So demonstrations have shown that high field bold activity closely track the position of neuronal firing and local field potentials. The relationship between stimuli and the bold response is often modeled using what's called a linear time invariant system, or an LTI system. Within this LTI system, the neuronal activity acts as the input, or the impulse, and the HRF acts as the impulse response function. So within this mathematical framework, the signal at time t, which I'm going to refer to as x of t here, is modeled as the convolution of a stimulus function, which I'm going to call v of t, and the hemodynamic response h of t. So that means that x of t is the convolution between v and h. Now what does that mean? Well, it means that the predicted bold response is going to depend upon what type of stimulus we perform. And that's fairly natural. So if we perform finger tapping for 20 seconds, resting for 20 seconds, we're going to get one type of predicted response. And if we clap our hands at random time points, we're going to get another type. So this example here shows how these things change. So let's suppose we have a block design, such as the finger tapping for 20 seconds, resting for 20 seconds, etc., etc. So we have an on-off type paradigm. What happens is we take this experimental stimulus function, and under the linear time invariant system, we convolve it with the hemodynamic response function. This means we take the hemodynamic response function and basically smooth this boxcar. We get a predicted signal like the green function in the panel to the left bottom. Now, if we instead have an event-related design, which is, just for sake of argument, say I clap my hands at random time points. So I have a very short stimulus, but lots of them. In this case, I convolve that stimulus function with the hemodynamic response, and I get something quite different. So the convolution is basically the smoothing of the experimental stimulus function by this hemodynamic response function shape. And so you see that depending on what type of experiment I perform, the predicted response will look quite different, as we see in these two panels at the bottom. This seems like a very convenient way of modeling the bold signal, but how good is it? Well, studies have shown that the bold response is roughly linear, with some departures from linearity. And there are some evidence of refractory effects, and what this is these are reductions in the amplitude of a response as a function of the interstimulus interval. And there's been some evidence of nonlinearity if the stimulus are spaced closer than 5 or 6 seconds apart. So if you make your stimulus too close to each other, then you might get some sort of nonlinearities. The fMRI signal is not as clean as I had in my little cartoon on the previous slides. The measured fMRI signal is corrupted by random noise and various nuisance components that arise both to hardware reasons, so the scanner, and to the subjects themselves. So sources of noise include thermal motion of free electrons in the system, the patient movement during the experiment, so if the patient moves back and forth, that causes noise. The subject gives rise to noise. The subject's heart rate and respiration causes physiological effects that corrupt the signal. And there's also something called a low-frequency signal drift, which we have to take into consideration. So slow changes in voxel intensity over time is present in the fMRI signal. And so these changes are very slow. So this is what we call a low-frequency type noise, and you see an example here to the bottom. And at first people thought that maybe this was due to subject motion or physiological noise, but then scientists put cadavers into the scanner and they still saw drifts. So now people think that this is due to scanner instabilities. But however, this is a very big source of noise, and we need to include drift parameters in our future models to incorporate this. Now, drift can have very serious consequences, and one is that experimental conditions that vary really slowly can potentially be confused with drifts. So basically, experimental design should use higher frequency, so more rapid alternations of stimuluses on and off states. So in the finger tapping, we shouldn't do 2 minutes of finger tapping and 2 minutes of rest, but rather we should do, say, 20 seconds of finger tapping, 20 seconds of rest more often. And the reason why the 2-minute design is not so good, you can see at the bottom here, because the typical signal magnitude, as you see at the bottom, is change in signal magnitude is quite small, and that's going to be completely drowned by this typical drift pattern. So we'll never be able to make out this signal due to the drift. Subject motion during an experiment is a huge source of problems in fMRI. And the reason is that we're usually studying time series from a single voxel, but if you move, the position of that voxel will change. And so you're basically, if you think you're tracking a single voxel across time, you might actually be tracking multiple voxels as you move. So typically motion correction is performed in the pre-processing stages of the analysis. However, even if you do a good job in doing that, you're still going to get something called spin history artifacts that are difficult to remove. And this is due to the fact that if you move, the slice of the brain that you're exciting at different time points is not really going to be the correct one, because if you move up and down, for example, you can get one part of the brain that's excited 2 slices in a row and whatnot. So this causes artifacts in the signal that we can't really remove by just simply correcting the position of the brain. And so usually we attempt to include motion parameters into our models. We'll talk about that as we move along. Let's start with the modeling stage of the course. Now, respiration and heartbeat give rise to what we call high frequency noise, because our heart might beat every second or so, or we might breathe every 2 seconds or so, and these sources of noise can potentially be modeled, but if the time resolution is too low, it's going to be difficult to do. So if we're only acquiring images every 2 seconds, it's going to be very hard to model something like heartbeat, which takes place every second or so. So for standard TR values, this type of noise is typically very, very difficult to remove unless you have measured it, using an outside source of measurement. You've hooked up some body scan or something like that. For these reasons, often left in the data and thus gives rise to temporal autocorrelations. So in general, some noise components can be removed prior to analysis, while others need to be included as components in subsequent models. However, as I said, it's difficult to remove or model all sources of noise, and therefore there's going to be significant autocorrelation in the resulting signal. And so in fMRI, we typically use what's called autoregressive or AR processes, or autoregressive moving averages or ARMA processes, to model the correlation. We'll talk a little bit more about that later on. Also, the spatial temporal behavior of these noise processes is complex. So here's a little illustration of a spatial map of the model parameters from what's called an AR2 model, estimated for each voxel's noise data. So basically these are just parameters of the noise process, and we'll see that by looking at these measured across the brain, we can make out spatial detail. And so depending on where in the brain you are, your noise might look quite different. Okay, so that's the end of this module. Here we've transitioned from talking about single images to talking about series of images or functional MRI images. And we talked about bold fMRI, and we've talked about the signal and noise properties of bold fMRI. Next week we're going to talk more about experimental design and pre-processing before we move on and start analyzing the data. Okay, I'll see you then. Bye.